Okay, this is going to be our last video for Chapter 5. We're going to talk about binomial expansion. We've technically discussed this topic before, but we called it a different name. Today we're also going to learn a shortcut for how we can make problems slightly easier. In general, binomial expansion refers to when we take a binomial, or something with two terms, and raise it to a power, but we don't have to necessarily do all the FOILing with our combining like terms and everything like that. The reason that we can take a shortcut is because of something called Pascal's triangle. This numerical pattern will allow us to determine the coefficients that are important when we expand terms out. So let's talk about what that triangle looks like. Pascal's triangle starts with a 1 in the first row and 2 ones in the second row. Because we want to create a triangle shape, there needs to be one more term in the following rows than there was in the previous row. So when we get to our third row of Pascal's triangle, we're going to have 3 terms. Now, to get to the missing term, or the stuff that's going to be on the inside, we need to add together the 2 terms that come above it. So 1 plus 1 gives us 2, and the third row is 1, 2, 1. There's always going to be 1s along the outside of the triangle. Our fourth row starts and ends with 1s, and to get our next terms, we add the numbers that are above to get 3 and 3. We start and end the row with 1, and to get the 3 terms that are now missing, we add the 2 that are above it to get 4, 6, and 4. We'll continue this pattern of adding the terms that are above and including 1s on the ends. Our next row would have 1, 6, 15, 20, 15, 6, and 1. And let's try to just fit in one more row. We'd have 1, 7, 21, 35, 35, 21, 7, and 1. Okay, again, this top represents row 0, or if we have a binomial raised to the 0 power. This second row represents raising our binomial to 1. If we squared our binomial, if we cubed our binomial, and so on. Okay, maybe take a second to pause the video and think, how are we finding those terms in Pascal's triangle to be able to fill out the entire thing? You would not be given this triangle, so you'll have to know how to recreate it yourself. Let's go ahead and talk about how we can connect the old method of expanding binomials with using Pascal's triangle in our new method. If this was the problem we were given and we needed to square this term, our old method would tell us to write it out twice. Writing it twice would show us that we need to FOIL to simplify. Starting with x times x, we would get x squared. X times y, we would just write xy. Y times x would be yx. And y times y would be y squared. Now, my second step would typically be to combine any like terms. Technically, these two are the same because they have the same variables, but just to emphasize that they're the same, I'm going to rewrite the second one so it looks like the first one. Okay, just flipping the order. I now can see that I have 2 xy terms. I have the y squared and the x squared on the ends, giving me my final answer. Now let's go ahead and connect this answer to Pascal's triangle. We raised our binomial to the power of 2, and so we're going to look at this row here, okay, our second row, to figure out our coefficients. Okay, we should have a coefficient of 1 on our first term, 2 on our second, and 1 on our third. If we look at our answer, there's technically an invisible 1, there's our 2, and another invisible 1 on the end, just like we want. Now, let's use the shortcut version instead of doing the foiling. Whenever you know what your exponent is for your binomial, you would start by writing those coefficient terms and leaving some blanks to fill in the rest. Okay, so we know second power will give us coefficients of 1, 2, and 1. What we're going to do then is consider how our first and second terms will change in terms of their exponents throughout the expression. The first term starts at the same exponent that the entire problem is being raised to and decreases as you go to the next term. So here we have x being squared. In the middle we would have x to the first power, and on the end we would have x to the 0 power. The opposite will be true for our second term. So we're going to start y at the 0 power and then increase it. Y to the first, and we'll end with y squared. If we simplify and rewrite, in the first term, the y to the 0 is gone. 1 times x squared is x squared. In the second term, both of our variables have an exponent of 1, which we don't necessarily have to write. And then in the third term, the x variable is canceled, and 1 times y squared is y squared. Okay. A slightly faster way to get the same answer as if we just FOILed. Now, foiling isn't super difficult if you just have 2 terms, but we're going to be looking at examples that have higher than degree 2, like this part A here. So let's go ahead and repeat the process for a 5th power. We're going to look at our 5th row and use these coefficients to start the problem. You might want to write kind of small so you can fit it all on your paper. We're going to have 1, 5, 10, 10, 5, and 1. Then we're going to go ahead and determine how the exponent on our first term is going to change in every step. We start with x to the 5th, start with the same exponent that the original problem has, and decrease as you go to the next terms. So then we'll have x to the 4th, x to the 3rd, x squared, oops, make sure you put the exponent on the outside, not the inside, x to the 1st, and then x to the 0. We know that'll eventually cancel out, but it's important to write it to keep organized. Then we're going to go to our second term. That one starts at 0 and increases as we go from term to term. So the next one will be 2 to the 1st, then 2 to the 2nd, 2 to the 3rd, 2 to the 4th, and we'll finish with 2 to the 5th. Let's go ahead and simplify each of these terms. In the first one, the 2 is gone, and 1 times x to the 5th gets us x to the 5th. In the second term, we'll have 5 times x to the 4th times 2, if we simplify this. In the third term, we'll have 10 times x cubed times 4 from taking 2 squared. In the fourth term, we'll have 10 times x squared times 8 from taking 2 cubed. Then we'll have 5 times x times 16 from taking 2 to the 4th. The x to the 0 will cancel, and 1 times 2 to the 5th is 32. Let's go ahead and take one more step to simplify any remaining terms. We're going to keep the x to the 5th. We'll have 5 times 2 to get 10x to the 4th, 10 times 4 to get 40x to the 3rd, 10 times 8 to get 80x squared, 5 times 16 to get 80x, and then plus 32. Here is our final answer for expanding x plus 2 to the 5th power. Although this might seem like a lot of work, this is much easier and much more organized than writing out x plus 2 5 times and foiling all of those pieces.